I just want to go on a rant about ML research and reproducibility. So recently I just had some time to go and look back at some applied research that I was doing, mostly because of what's going on in the tech sphere and whatnot, but that's neither here nor there. But the story is 2 years ago, a colleague and we were trying to reproduce the results of this particular paper, this feature tweaking paper, because it was actually a very interesting paper. So I'm going to quickly go through it. I want to talk about like some of the things we observed when we were trying to reproduce it and my recent attempts at thinking about how we can do it better. So this paper, the idea is fairly straightforward, despite it being like a ML paper. It is from KDD. It's a data mining paper, to be clear. And the reason why I'm saying that will become evident in a little bit. So the high level idea for this paper is we have an ensemble of decision trees, right? And we have a feature vector, which is just the inputs for a decision tree, right? And the idea is we want to we want to modify the features in the most minimal kind of way so that we flip the label. That's what all of this mumbo jumbo in this for loop is. So we're trying to find, where you can see my mouse, the optimal transformation with respect to a delta. So this delta is like the delta ball that you might see in university mathematics, such that the label is flipped. So the idea is not particularly tricky. You essentially go from where the leaf node is, and you can traverse up and down the tree to find like what is the minimal perhaps distance with respect to the leaf node, or with respect to the feature that would cause it to perhaps go up or traverse the tree in a way that will end up flipping the label. And the high level idea is you want to find it in a way that satisfies this delta. So that's why they have this epsilon thing. And the other thing is you also need to then go and check and evaluate with respect to the whole like global ensemble of trees as well, because there may be a scenario where just because you check the kth decision tree and you can see that it's like checking the set of positive paths, that you end up in a scenario where this doesn't work. And this is not evident in the algorithm itself. In fact, the only way you can really spot it is if you jump to the conclusion where it ends up saying, oh, despite computationally intractable in the worst case. Well, that's not very helpful because there's no guarantees here, right? Like you might be able to never find a scenario where you end up flipping the sign within this delta ball. In fact, it is impossible to really have like a particular delta or an epsilon that would guarantee this kind of flipping. And this isn't just because of not being able to find a part in the tree that you can traverse up and flip it. It's just the nature of an ensemble. It's like one tree may say one thing, but then when you look at it from a global perspective, well, maybe all the other trees disagree, and then, well, you're screwed. So this idea was something that we found when we were trying to apply it to the data sets that we had. So, to be fair to the authors of the paper, which is from Yahoo Research, they're working with ads and that kind of data set. And those kinds of data sets, I would argue, are actually far easier than perhaps like a data set that is related to, say, risk or something like that. And the reason is that the way that you frame something that is typically to do with ad spend or like uplift or marketing is that you have a lot of signals that may be weakly correlated, but you have a lot of them. So I think to be able to flip a signal there and to then use that to justify some kind of outcome is pretty straightforward. Well, I shouldn't say pretty straightforward, but there's like more avenue for that. So I think it's generally because, at least from my perspective, that kind of problem is a bit simpler. You don't have a scenario where you have insanely imbalanced labels or anything like that. So whereas the realm that I generally work with is in risk, and in those particular cases, the decision boundary, if you like, is far more nuanced. Normally the labels are highly imbalanced, and to get it to flip, well, you get some really wacky results, or you have some results where it doesn't work as well. And in fact, we found that more often than not, we just could not find an appropriate way to flip the label for a multitude of examples. So what I came across recently, or was thinking about recently, was rather than using, say, a decision tree in this kind of way, like a generic decision tree specifically, maybe there's other ways of how we can try to flip the label and have perhaps better guarantees for how this might look like. And the approach that I thought of was to use a lesser known algorithm, but from a group that I deeply respect, which is called the Optimal Sparse Decision Trees. And this is from a group that is led by Cynthia Rudin, who I think I came across her research maybe around 2017 as well. And I think like 2017-ish, and I think she has some talks that are a little bit after that, where she makes the case for interpretable ML can be done in a way that is competitive with like the more typical case, like your boosting machines and whatnot. And the typical cases that came up in the more recent papers, by recent I mean like post 2020, is around this like optimal sparse decision trees, and the name itself tells you what it does. It's trying to find a tree that is sparse and covers a lot of ground, and the way that they build it is that these trees may not necessarily be built in a greedy way. That's why there's a optimal side. That's why there's optimal in the name of the optimal sparse decision tree. So that's the OSDT. Now, why am I bringing up this algorithm? It's not just because that it's a cool algorithm. It is a cool algorithm. The reason why I bring it up goes back to the first thing I said today about the reproducibility challenge with these papers. And the easiest way to show you this is that they had a very recent paper, or relatively recent, at least in the NeurIPS 2022. And the crazy thing when I came across this paper, and this is one of those things that LLMs do really well, it's like related to the video that I said, my last video with Dan Liu talking about like optimality and what kind of cases software can be used to build effectively using LLMs. This is one of them, right? And I think this bit, and it shows, this is the paragraph that is on my mind, and it shows like the difference between researchers and engineers. They built it on top of an existing package, and the algorithm that they introduced in this particular paper, well, they just replaced the actual algorithm. It's using the same name. It's using GOSDT, which is a global optimal sparse decision tree, and this is a reference paper that implements this GOSDT. So what this means is, well, if you're in a situation where you want to compare both of these algorithms, well, you can't import both of them, or in fact, it's difficult to import both of them because they share the same name and they're just built on top of the same like repository, right? Like this one is literally a fork of this paper, and this is like the craziness with like reproducibility. How do you know, or how can you approach it in a way that is easy to do when you're an applied ML practitioner, right? Like you're in a position where you don't really care about the intricacies of research necessarily. You just want to apply these algorithms. You want to use them in your day-to-day because you've read about them and you feel that they're effective. Whereas from a research perspective, it's like once you write the paper, you publish the algorithm, that's it. And maybe there's like this marketing thing that is like the gap between industry and academia. But I think this was a bit that made me very annoyed. Not so much, and it's just more a reflection of academia and research. Reproducibility is not being annoyed at the researchers themselves. I think me having done like this kind of research before, I totally understand like the types of incentives that people have. But it made me annoyed in the sense that like if I was to promote these algorithms to the wider world. Let's say that I'm an influential person in ML space. I was like, oh, these algorithms are great. You should go out and use them. Well, you can't use both of them. You can only pick one because they share the same namespace when you go and try to install it following the instructions. And I think this is a thing that, like, as a whole, the industry, the academia side of things rather, hasn't done a particularly great job. Now, back to the actual application at hand that I was trying to show. Why was I interested in like these kinds of algorithms, the optimal sparse decision tree? Now, because I thought that because these were not built in a greedy way, it meant that there would be less nodes. Well, that's why they're called sparse, and they'll be informative. Like oftentimes in a decision tree, especially when you build like a random forest, I think random forests are particularly susceptible. I think GBMs normally, like gradient boosting machines, that's GBMs, generally have a smaller depth than random forests. Like random forests can just grow really, really long, and they just maybe take one feature, and there's like multiple branches that just chop up that same feature many times. And what happens there is when you go, and this was like my hypothesis at least, if we were to go and use this feature tweaking approach, right, like this part, the traversal part for all the paths for the kth decision tree, this is a bit that gets very expensive. So if we have a sparser tree that doesn't have as many cuts, I suppose, or as many decision points because they're built in a non-greedy kind of way, or maybe it's easier to find a particular path that will succeed. And I think like when I did my experiments, like just to cut to the chase, this idea did seem to work. And I just wanted to show like even though this algorithm, this feature tweaking algorithm is fairly simple, even on fairly small data sets, there's still a lot of computation, which is something that's on my mind about like how well or how universally can we apply feature tweaking to a general data set. I think it's actually kind of difficult. So I have this example here. So this is using a breast cancer data set, and it's just using like 40 samples each. Now, the thing with the breast cancer data set is, so this is part of the scikit-learn, and you can see that there's only 30 features here. And even though there's only 30 features and we're like taking a sample of 40, it's like you're still doing like thousands and thousands of iterations and thousands of tests or sampling just to find a flip. And I think this is like this is a kind of challenge with this kind of problem, that even the small scenarios, you are doing a lot of perhaps unnecessary compute, maybe depending how you're framing it. But it was definitely interesting testing this on synthetic data sets. I did get a much better hit rate of the synthetic data sets and also the breast cancer data set. So I called it, so these algorithms are actually the tree farm algorithm, which is from here. And you can see that like I got 100% of the time it managed to find a particular node that it would work. Like tree farm, to be clear, I skipped over or glossed over the detail of tree farm, but the whole idea is that it finds a set of optimal trees. So it doesn't just find one optimal tree, it finds a whole set of optimal trees. And what this meant, and to be clear, this is like one single decision tree. What this meant is that if we were to look over the set of decision trees that would solve a particular classification problem, or rather supervised learning problem, if we wanted to find a flip in the sign, you should be able to find one over the set of trees that you built. So that was a high-level idea, and it fared much better. Now, when you convert it to a random forest, just to explain the issue with this algorithm, yeah, you then have problems. So for all the synthetic set, yeah, I still got 100% pass rate, but off the breast cancer set, I only got a 15% pass rate. And this is the thing that like drives me really, really crazy with these kinds of like reading these research papers. It's like, whilst on one hand, synthetic data sets, yes, it passed 100% of the time, to then use it on a fairly like stock standard data set and only have 15% of the time following the algorithm as a random forest, passing it with this kind of like sparse decision tree really makes me wonder like what kind of problems that they must have had for it to work successfully. Because like, again, breast cancer is not a complicated data set. And even then, I had a massive challenge in trying to apply this. Now, again, I just want to stress, this is not a fault of the algorithm, because clearly there are particular scenarios like this synthetic scenario where it worked well. And also, again, it's not like the researchers were hiding anything necessarily. Maybe you could argue that they weren't showing the full picture about like how successful it was or whatnot. They did point out in like this one line that, well, it may be computationally intractable. But yeah, it's surprising to me that that it would fail so often, or at least when I tried a random data set. This is a kind of difficult problem, to be fair. They also indicate that it is NP hard, and it is. You can't, like verifying whether a particular feature when tweaked is validly like flips the label is not something, it is definitely an NP hard kind of problem. But yeah, and I think it is for this reason we don't see this approach in practice. I think if it was a successful approach, probably a lot of people would be talking about it a lot more. I think like this kind of like causal way of thinking about ML is a very powerful one that you don't see enough about. I think people rely too much on things like SHAP values because it just works out of the box. You just do pip install SHAP or whatnot, and then all of a sudden you get the answer, or even now comes baked into like GBM and XGBoost. I would love to see more of this like causal kind of research work well just out of the box. That would be amazing to see for someone who's just doing applied research. And the other thing that I would love to see is like these kind of algorithms that tackle like real world challenges. I think like the optimal sparse decision trees, for example, like some of the outputs I've got out of that are actually very, very interesting, right? Like the fact that you can get like replicating a massive ensemble of trees with a much simpler decision tree is an amazing kind of outcome. People don't normally visualize like a GBM tree, or rather GBM trees, right? If you build 100 trees over like 1,000 features, you're not going to be able to visualize and be able to wrap your head around how do you pass the things through all the values. But if you have a tree that is built in an optimal way, that is non-greedy, that recovers like a lot of the performance of those kinds of more complex ensembles, it is something that is much more interpretable and actionable, and where you can start to draw causal kinds of ideas. And that's something I would love to see more in like applied research that people don't talk about. Anyway, that's my rant about research and reproducibility, and how it's very difficult to use like code that researchers have done, or at least in this case there is code. Like the feature tweaking, there is no code for that. You just throw it in an LM and hope for the best, or you write it by hand. And yeah, it's going to be a challenge in these kinds of instances. Well, in these cases, these are from big labs and big companies, right? Yahoo Research and this particular lab. There are other scenarios where there are no like reputation or anything like that you can rely on to even expect that the paper is reproducible at all. Sometimes you just go in and try something and it just doesn't work, and you don't know whether it's your implementation, your understanding of the paper, or that the paper has flaws. It's a very difficult kind of problem, and I think it's something pretty universal in this field, unfortunately. But it's something that is part of the game, and it's just part of the fun. Anyway, that's what I have for you. That's my little rant of the day and my little journey in this kind of ML research space that I genuinely find interesting, and I come back to it every now and then when I have time. With that, thanks for watching. If you make it to this stage of the video, do really appreciate it. I find it crazy that there are people listening to me rant about these topics, so I'm just going to keep doing it. For me, this is therapy. Thanks.